Chapter 5 The Distribution Law 5.1 Introduction Definition of the Distribution Law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids, in both of which it is soluble, it distributes itself between the two liquids in such a manner that the ratio of concentrations of the substance in the two liquids is always constant at constant temperature. These observations were made by Berthelot and Junkfleisch in 1872. However, it was pointed out by Nernst in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight in both the solvents. Hence, the generalization was put in a proper form by Nernst and is called Nernst distribution law. It states as follows: a solute distributes itself between the two immiscible solvents in such a way that the ratio of the concentrations of the solute in the two solvents is constant at constant temperature, independent of the presence of any other molecular species, provided that the solute has the same molecular state in both the solvents. Thus, if a solute X distributes itself between the two immiscible solvents A and B, then if X remain in the same molecular state in both the solvent, we will have concentration of X in solvent A by concentration of X in solvent B is equal to C1 by C2 is equal to K, a constant. The constant K is called distribution coefficient or partition coefficient. To test the validity of the law, different amounts of a solution of iodine may be added to a mixture of water and carbon tetrachloride taken in different bottles. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hyposolution to find out the concentration of iodine. Similar experiments may be performed with other solutes and immiscible solvent. 5.2 Conditions under which distribution law is valid. The distribution law is valid only if the following conditions are satisfied. First, the temperature must remain constant throughout the experiment. Second, the two liquids should be mutually immiscible. Third, the amount of solute added should be small, that is, the solution should be dilute. This is essential because in certain cases, the solute added affects the mutual solubility of the solvents. Fourth, the solute must have the same molecular state in both the solvents, that is, it should not undergo association or dissociation in any of the solvents or combination with any of the solvent. Thus, the law is not valid for the distribution of benzoic acid between water and benzene because it has been observed that in benzene, benzoic acid undergo association to form dimers. Similarly, the law is also not valid for the distribution of any electrolyte between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolyte undergo dissociation in water. Next, 5.3 Thermodynamic derivation of the distribution law. The thermodynamic derivation of the distribution law is based upon the principle that if there are two phases in equilibrium, that is, two immiscible solvents containing the same solute dissolved in them, the chemical potential of a substance present in them must be same in both the phases. From thermodynamics, we know that the chemical potential of a substance in a solution is given by mu is equal to mu naught plus RT into ln of A, where mu naught is the standard chemical potential and A is the activity of the substance in the solution. Thus, for the solute in liquid A, we have mu A is equal to mu naught A plus RT into ln of A or A. Similarly, for solute in liquid B, we have mu B is equal to mu naught B plus RT into ln of AB. But as already stated, since the liquid A and B are in equilibrium, then mu A is equal to mu B. On solving the equations, we get ln of activity of A by activity of B is equal to mu B naught minus mu A naught by RT. Further, at a given temperature, mu A naught and mu B naught are constant for given substance in the particular solvent. Hence, at constant temperature, we have from equation ln of activity of A by activity of B is equal to constant, and therefore activity of A by activity of B is constant. This is the exact expression for the distribution law. However, if the solutions are dilute, the activities are equal to the concentration, so that the expression is modified to concentration of A by concentration of B is equal to constant, which is the original form of the distribution law. 5.4 Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out the distribution law in the form C1 by C2 is equal to constant is applicable only if the solute remains in the same molecular state in both the solvents. That is, it does not undergo association or dissociation in any of the solvents or combination with any of the solvents. If, however, such changes take place in any of the solvents, then the law cannot be applied to the total concentrations of the solute in the two phases, but only to the concentrations of the identical molecular species in the two phases. In each of these cases, the distribution law equation is modified as discussed below or a few simple cases. Case 1. When the solute undergo association in any one of the solvent. Suppose the solute X remains in the normal molecular state in phase 1, but an molecule of it associate to form complex molecule Xn in phase 2. Then the following two equilibrium will exist simultaneously. First, X in phase 1 is in equilibrium with X in phase 2. Second, Nx is in equilibrium with Xn in the same phase 2. Suppose the total concentration of the solute X in phase 1 is equal to C1 and total concentration of solute X in phase 2 is equal to C2. Also suppose alpha is the degree of association of solute in phase 2, then concentration of the associated molecule in phase 2 is equal to 1 by N into C2 alpha, and concentration of the unassociated molecules in phase 2 is equal to 1 minus alpha into C2. Applying the distribution law to equilibrium first, we get concentration of solute X in phase 1 by concentration of normal molecules of X in phase 2 is equal to constant. That is, C1 by 1 minus alpha into C2 is equal to constant. Again, applying the law of chemical equilibrium to equation 2, we get concentration of associated molecules in phase 2 by concentration of normal molecules in phase 2 raised to the power n is equal to constant. That is, C2 alpha by 1 minus alpha into C2 whole power n is equal to constant. On taking nth root and dividing the equations, we get C1 by under root of nth C2 into alpha is equal to constant, which is the exact formula. When the molecules in phase 2 are almost completely associated, that is alpha is equal to 1. Therefore, C1 by nth root of C2 is equal to constant. Alternatively, the same result may be obtained in a simple manner as follows. Suppose concentration of solute X in phase 1 is C1. Concentration of associated molecules in phase 2 is equal to C2 and concentration of simple molecules in phase 2 is equal to C3. Applying the distribution law of equilibrium, we get C1 by C3 is equal to constant. Again, applying the law of chemical equilibrium to equation 2, we get C2 by C3 whole power n is equal to constant. On taking nth root of both sides, we get nth root of concentration of C2 by C3 is equal to constant, and on dividing the equation 3 by equation 4, we get C1 by nth root of C2 is equal to constant, which is the same as derived above. Thus, in such cases, when the solute undergo association in one of the solvent, the constant value for the partition coefficient is obtained not for the ratio C1 by C2, but for the ratio C1 by nth root of C2. This relationship has been confirmed by studying the distribution of benzoic acid between water and benzene. The acid existing mainly as associated molecule in benzene solution. The formula C1 by nth root of C2 is equal to K is commonly used for finding the value of N, that is, the extent of complexity of the solute molecule in one of the solvent. This is done by finding out the concentration C1 and C2 of the solute in the two solvents in a number of experiments. The value of N is then calculated as explained later. Case 2. When the solute undergo dissociation in one of the solvents. As before, suppose the solute X dissolved in phase 1 without any change in the molecular state, but under dissociation into Y and Z, etc. in the phase 2. Then, as shown in figure, the following two equilibria will set up. First, X in phase 1 goes in equilibria with X in phase 2. Second, X dissociates to give Y plus Z in the same phase 2. Suppose the total concentration of solute X in phase 1 is equal to C1 and total concentration of solute X in phase 2 is equal to C2. Also suppose the degree of dissociation of the solute in the phase 2 is alpha, then concentration of undissociated molecule in phase 2 is equal to 1 minus alpha into C2. Applying the distribution law to equilibrium, we get C1 by 1 minus alpha into C2 is equal to K. Note, it is obvious that if the solute undergo dissociation in phase 1 with degree of dissociation is equal to alpha but remains normal in phase 2, then the formula obtained will be C1 into 1 minus alpha by C2 is equal to K. Similarly, if the solute undergo dissociation in both the phases with degree of dissociation is equal to alpha in each case, then the formula will be C1 into 1 minus alpha by C2 into 1 minus alpha is equal to K. From the above expression, the degree of dissociation alpha can be calculated. Case 3. When the solute undergo combination with one of the solvents. Suppose the solute X remain in the normal molecular state in phase 1, but one molecule of it combines with n molecule of the solvent S to form the compound molecules X dot Ns in phase 2. Then, as shown in figure 5.5, the following two equilibria will be established. First, X in phase 1 is in equilibria with X in phase 2. Second, X plus Ns is in equilibria with X dot Ns in the same phase 2. Suppose concentration of solute X in phase 1 is equal to C1. Concentration of normal molecules in phase 2 is equal to C2. Concentration of solvent molecules in phase 2 is equal to Cs, and concentration of compound molecules in phase 2 is equal to Cc. Applying the distribution law to equilibrium, we get C1 by C2 is equal to K. Again, applying the law of chemical equilibrium, we get Cc by C2 into Cs to the power n is equal to K1. Since the solvent in phase 2 is present in excess, its concentration remains almost constant in spite of combination with the solute X, particularly if the solute is added in small quantity, that is, the solution is dilute. Then Cs to the power n is constant, and so the equation becomes Cc by C2 is equal to K1 into Cs to the power n is equal to K2 and another constant. Adding 1 to the both sides, we get C2 plus Cc by C2 is equal to 1 plus K2. On dividing the equation with the above equation, we get C1 by C2 plus Cc is equal to K by 1 plus K2, which is equal to K3 and another constant. But C2 plus Cc is the total concentration of the normal as well as the solvated molecules of the solute X in phase 2. Thus, the above equation in fact implies that total concentration of solute X in phase 1 by total concentration of solute X in phase 2 is equal to constant. Hence, we conclude that when the solute enters into chemical combination with one of the solvents, there is no modification of the distribution law equation except that the numerical value of the partition coefficient is changed. 5.5 Applications of distribution law. The distribution law has been applied to the study of problems of both theoretical and practical interest, a few of which are briefly discussed below. First, in calculating the solubility of a solute in a solvent. When the two immiscible solvents are in contact with each other and the solute is added in such a large excess that saturated solutions are formed, then the concentrations of the solution at this stage will be equal to their stabilities. Assuming that the distribution law is applicable for such concentration, we will have C1 by C2 is equal to S1 by S2 is equal to K, where concentration C1 is equal to S1 is the solubility of the solute in solvent 1 and concentration C2 is equal to S2 is the solubility of the solute in solvent 2. Thus, knowing the distribution coefficient K and the solubility of the solute in one of the solvents, that in the other can be calculated easily. Second, in studying the extent of association or dissociation of the solute A in a solvent, we have already seen that when a solute undergoes association in one of the solvent in which its total concentration is C2 and has the normal molecular state in the second solvent in which its concentration is C1, then distribution law formula is modified to C1 by nth root of C2 is equal to K. From this formula, the value of n can be calculated either by hit and trial method or by logarithm method as explained before. First is hit and trial method. The values of C1 and C2 obtained in different experiments are put in the equation C1 by nth root of C2 is equal to K. Then putting n is equal to 2, 3, 4 etc. one by one, the values of K are calculated in each case. The number which give constant value for K is the correct value for n. Second is logarithm method. The formula for finding n is C1 by nth root of C2 is equal to K. So on solving the equation, we get n is equal to log C2 minus log C2 dash by log C1 minus log C1 dash. Hence n can be calculated easily. Similarly, when a solute undergoes dissociation in one of the solvents in which its total concentration is C2 and has the same normal molecular state in the second solvent in which its concentration is C1, then we have C1 by C2 into 1 minus alpha is equal to K, the distribution coefficient. From this formula, the degree of dissociation alpha can be calculated easily. Third is in predicting the distribution indicators. It has been seen that iodine distributes itself between CS2 and water with a distribution coefficient equal to 400 towards CS2. Thus, if a weak solution of iodine is to be estimated, then a few drops of CS2 may be added to this solution. As a result, a considerable amount of I2 will pass into CS2 layer and give it a deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Thus, iodine acts as a distribution indicator in this case. Fourth is in the study of chemical equilibria leading to the formation of complex ion. Example, Ki plus I2 gives out Ki3. Kbr plus Br2 gives out Kbr3 and so on. Distribution law helps us to determine the equilibrium constant for any of the above equilibrium reactions, and hence to establish the formula of complex ion on the basis of the constancy in the value of equilibrium constant. As an example, let us consider the first equilibrium reaction. To study of this equilibrium involves the following step. First, a solution of iodine in CS2 is shaken with water to find out the distribution coefficient of iodine between water and CS2. Second, a solution of iodine in CS2 of known concentration is shaken with Ki solution also of known concentration. Third, after the distribution of iodine is complete between the two layers, the concentration of iodine left in the CS2 layer is determined by titrating against standard hypo solution. The result is then calculated as follows. Suppose that initial concentration of iodine in CS2 is A moles per liter and initial concentration of Ki solution is equal to B moles per liter. Concentration of I2 left in CS2 layer after distribution is equal to C moles per liter, and distribution coefficient of I2 between water and CS2 is equal to K. As iodine reacts with Ki, the total concentration of iodine, that is free plus combined, in the aqueous layer is much higher. Obviously, total concentration of iodine free plus combined in aqueous layer is equal to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer, that is A minus C moles per liter. Concentration of free I2 in aqueous layer can be calculated by applying distribution law, that is concentration of free iodine in aqueous layer by concentration of iodine in CS2 layer is equal to K. But concentration of iodine in CS2 layer is equal to C moles per liter and concentration of free iodine in aqueous layer is equal to Kc moles per liter. So amount of iodine that has combined with Ki is equal to A minus C minus Kc moles per liter is equal to D moles per liter. Now according to the reaction, Ki plus I2 gives out Ki3. Number of moles of I2 combined is equal to number of moles of Ki combined plus is equal to number of moles of Ki3 formed. That is, concentration of Ki3 in the aqueous layer is equal to D moles per liter, and concentration of Ki in the aqueous layer is equal to B minus D moles per liter, and concentration of I2 in the aqueous layer is equal to Kc moles per liter. Substituting these values in the equilibrium law expression, the equilibrium constant K dash can be calculated. Starting with different initial concentrations of iodine and Ki solution, the value of K dash is determined in each case. A fair constancy in the value of K dash confirms the formula of the complex or that of the complex ion. Next is fifth, in the process of extraction. The process of extraction is of great importance both in the laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvents like ether, chloroform, carbon tetrachloride or benzene. In the industry, the process is used to remove the impurities from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with water, but in which the substance to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substance passes into the organic layer, from which the former can be separated out by distilling of the organic solvent. However, in order that the process of extraction may be more efficient and effective, the following two conditions must be fulfilled. First, the value of distribution coefficient of the substance between water and the extracting solvent should be greater in favor of the extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in aqueous phase. This can be done by adding some substance which depress the electrolytic dissociation of the compound being extracted. Thus, Suppose that an organic acid which ionizes to a certain extent in aqueous solution is to be extracted with ether. If a strong inorganic acid is added to the solution, the hydrogen ion concentration is increased and the ionization of organic acid is reduced because of common ion effect. In the solution, there will be greater amount of the undissociated acid and hence the amount extracted will be greater. Similarly, an organic base can be best extracted in the presence of a strong inorganic base. The addition of salts also usually lower the solubility of an organic compound in water and thus increases the distribution coefficient. Second, the whole of the extracting solvent should not be used in one lot but it should be used in maximum number of installments. That this factor increases the efficiency of extraction can be seen as follows. Suppose X gram of the substance are present in 1 liter of the aqueous solution. Also suppose 1 liter of ether is available as the extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now if whole of the ether is used in one lot and X gram with the amount of substance extracted into the ether, then we will have concentration in ether by concentration in water is equal to X by 1000 by X capital X minus small x by 1000 is equal to 2. So here small x is equal to 0.67x. Thus only 67% of the total amount will be extracted in this case. Again, suppose the whole of the ether is used in two installments, each of 500 cm cube. After shaking with the first installment of 500 cm cube, suppose x1 gram of the substance passes into the ether layer, then clearly x1 by 500 by capital X minus x1 by 1000 is equal to 2 or x1 is equal to 0.5 capital X. Thus 50% of the total amount is extracted out in this operation. Therefore, the amount of substance left unextracted is equal to capital X minus half of capital X is equal to half x. Now 1 liter of the aqueous solution containing half x gram of the substance is shaken with the remaining 500 cm cube of ether. Suppose the amount extracted into ether by this operation is x2 gram. Then x2 by 500 by capital X by 2 minus x2 by 1000 is equal to 2 or x2 is equal to 0.25x. That is 25% of the total substance passes into the ether layer in this operation. Therefore, total amount of the substance extracted is equal to 50 plus 25 is equal to 75%. Thus, when a 1 liter of ether is used in two equal installments, the percentage extraction increases from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used in 4 equal installments. The extraction increases to 93.75%. A general formula can be derived which gives the amount of substance left unextracted after a definite number of operations. Suppose W gram of substance is present in V ml of the solution made in solvent A. Also suppose that V ml of the extracting solvent B is used each time and the K is the distribution coefficient of substance between the solvent A and B. Now if W1 gram be the amount of substance left unextracted in solvent A after the first operation, then concentration in A by concentration in B is equal to K. That is K into W minus W1 by small v is equal to W1 by capital V. On solving the equation, we get W1 is equal to Kv into W by small v plus Kv. Again, after the second operation, if W2 be the amount of the substance left unextracted in solvent A, so that amount extracted is W1 minus W2 gram. Then W2 by capital V by W1 minus W2 by small v is equal to K. On solving equation, we get W2 is equal to Kv by small v plus Kv into W1. Putting the value of W1 from above equation, we get W2 is equal to Kv by small v plus Kv whole square into W. In general, after nth operation, the amount of the substance left unextracted will be Wn is equal to Kv by small v plus Kv to the whole power n into W. In order that the extraction may be most efficient, clearly Wn should be smallest possible. This can be so only if the factor Kv by V plus Kv to the whole power n is as small as possible. Now in this factor, the denominator small v plus Kv is greater than the numerator Kv. Therefore, Kv by small v plus Kv is less than 1. Hence, the above factor will be the smallest possible when n is the largest possible. So, it follows that the multi-step extraction is more economical than the single-step extraction. Further, from the above equation, it may be seen that Wn can never be equal to 0, howsoever large n may be. In other words, extraction can never be complete, howsoever large number of extractions may be carried out. Otherwise, so it is clear that every time the substance left distribute itself between the two solvents, some quantity, howsoever small, must be left unextracted. The principle of multi-step extraction holds good for washing the precipitate, whereby the impurity distribute between the liquid and the precipitate. Further, in Parquet's process for desilverization of lead also, use is made of the principle of extraction. Silver is more soluble in zinc than in lead. Zinc is immiscible with molten lead. Thus, when zinc is added to argentinoferrous lead, a large quantity of silver goes into the molten zinc layer, leaving little silver in the solution in molten lead layer, because the distribution coefficient of silver between zinc and lead is 300 at 880 degrees Celsius. Zinc containing silver from the upper layer. Thus, by repeating the process, almost total quantity of silver can be extracted from argentinoferrous lead. Sixth is in the determination of degree of hydrolysis. Let us first study some terms and expressions related to salt hydrolysis. Hydrolysis constant. The general equation for the hydrolysis of a salt may be written as Ba plus water gives out Ha plus BOH. Applying the law of chemical equilibrium, we get concentration of Ha into concentration of BOH by concentration of Ba into concentration of water is equal to K, the equilibrium constant. Since water is present in very large excess in the aqueous solution, its concentration may be regarded as constant, so that we have a concentration of Ha into concentration of BOH by concentration of Ba is equal to K into concentration of water is equal to Kh, where Kh is called the hydrolysis constant. Since concentration of Ha and concentration of BOH represent the molar concentration of free acid and free base produced, and Ba represent the molar concentration of unhydrolyzed salt, the above expression for the hydrolysis constant may be written in more general way as Kh is equal to concentration of free acid into concentration of free base by unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction of the total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride, 90% of the salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.90 or may be expressed as percentage. It is usually represented by the symbol H. That is, H is equal to number of moles of the salt hydrolyzed by the total number of moles of the salt taken. Expression for the degree of hydrolysis for solutions of different kinds of salt. As salts of strong acid and bases do not undergo hydrolysis, therefore to talk of KH or H for such salt is meaningless. That The cases of the other three types of the salt are discussed below. First, salt of weak acid and strong base. Representing salt by Ba as usual, the hydrolysis may be represented as follows. Ba plus water gives out BOH plus Ha, or Ba positive plus A negative plus water gives out B positive plus OH negative plus Ha. On cancelling out, we get A negative plus water gives out OH negative plus Ha. That is, it is a case of anion hydrolysis. Suppose the original concentration of the salt in the solution is C moles per liter and H is its degree of hydrolysis at this concentration. Then we have A negative plus water gives out OH negative plus Ha. On calculating the hydrolysis constant, we get the value of hydrolysis constant as CH square by 1 minus H. If H is very small as compared to 1, we can take 1 minus H equivalent to 1, so that the above expression becomes CH square is equal to KH and H is equal to under root of KH by C. That is, H is inversely proportional to the concentration of 1 by 2 concentration. Thus, the degree of hydrolysis of a salt of a weak acid and a strong base is inversely proportional to the square root of its molar concentration. Second, salt of strong acid and weak base. For such a salt Ba, the hydrolysis may be represented as Ba plus water gives out BOH plus Ha. Here, our base is weak and acid is strong. So we get B positive plus water gives out BOH plus H positive. That is, it is a case of cation hydrolysis. Proceeding as in earlier cases, we get the same relationship. H is equivalent to under root KH by C. Third is salt of weak acid and weak base. Representing the salt by Ba, as before we have Ba plus water gives out BOH plus Ha. That is, B positive plus A negative plus water gives out BOH plus Ha. That is, it involves both anion hydrolysis as well as cation hydrolysis. In this case, we have the original concentration of B positive and A negative as C and concentration at equilibrium as C into 1 minus H. So on calculating the hydrolysis constant, we get KH is equal to H square by 1 minus H whole square. Here the relationship between KH and H does not involve C. Thus, degree of hydrolysis of such a salt is independent of the concentration of the C. If H is very small in comparison to 1, we can take 1 minus H equivalent to 1, so that the equation becomes as KH is equal to H square. That is, H is equal to under root of KH. Determination of degree of hydrolysis by the application of distribution law. Suppose it is required to determine the degree of hydrolysis of an aniline hydrochloride, which is a salt of a weak base and a strong acid. The method consists of two steps as follows. Determination of the hydrolysis constant. Aniline hydrochloride is hydrolyzed as aniline hydrochloride plus water gives out aniline plus water plus HCl. The hydrolysis constant will therefore be given by KH is equal to concentration of free aniline into concentration of free HCl acid by unhydrolyzed salt. Thus, to get the value of KH, the aim is to find the molar concentrations of free aniline, free HCl acid and the unhydrolyzed salt in an aqueous solution of aniline hydrochloride. This is done by shaking aqueous solution of aniline hydrochloride of known concentration with benzene. As a result, the free aniline distributes itself between the two solvents, that is water and benzene, whereas HCl acid and the unhydrolyzed salt remain in the same aqueous layer only as shown in the figure. First is calculation of concentration of free aniline in the aqueous layer. For this purpose, the concentration of aniline present in the benzene layer is found by taking a known volume of this layer evaporating of the benzene and finding weight of aniline left. Having known the concentration of aniline in the benzene layer, that in the aqueous layer can be calculated if the distribution coefficient of aniline between water and benzene is known, which can be found by a separate experiment. Second, calculation of concentration of free HCl produced. From the hydrolysis equation, number of mole of HCl produced is equal to total number of moles of aniline produced. But the total amount of aniline produced is equal to amount of aniline present in benzene layer plus amount of aniline present in aqueous layer. Each of these amount has already been calculated in step A above. Hence, the total number of moles of aniline produced and hence the free HCl produced can be calculated. Knowing the volume of the aqueous layer, the concentration of free HCl in the aqueous layer can be calculated. C. Calculation of the concentration of the unhydrolyzed salt. From the hydrolysis equation, it is clear that the number of moles of the salt hydrolyzed is equal to the total number of moles of the aniline produced or free HCl produced, which has already been calculated in step B above. Hence, knowing the initial number of moles of the salt taken, the number of moles of the salt left unhydrolyzed can be calculated. Further, knowing the volume of the aqueous layer, the concentration of the unhydrolyzed salt can be calculated. Second, calculation of degree of hydrolysis. Knowing the hydrolysis constant Kh, the degree of hydrolysis of a solution of aniline hydrochloride having concentration C moles per liter can be calculated directly from the expression H is equal to under root Kh by C. Thank you.